Good evening, guys. Can you guys hear me?
Yes.
Yeah.
Yes.
Yeah.
Great.
Yes.
How's everybody doing so far?
Good, and yourself?
Yeah, I'm doing good too. Thank you for asking. Okay, before we start today's lecture, any questions, concerns, issues you guys would like me to address? Okay, so if there are no other questions, then we can start today's lecture session. And this week we didn't have any lab sessions, review sessions, just because I wanted you to focus on your project and whatever the things that have been assigned to you. So you will continue working on that. So we will have the lab review sessions or the project review sessions in the lab timings from the next week onwards. So today, what I would like to begin with is a SolidWorks tutorial, again, a short tutorial on finite element simulation using SolidWorks. So I uploaded some few parts or few model in SolidWorks. So if you have access to Beachboard, you can download them and you can also open them and you can work on it simultaneously, or at least you can look at the screen what I'm showing to just show you a short tutorial about how to run the simulations for analysis steps, or for assembly, not for analysis, but for assemblies. So what we have seen so far is running simulation using parts, single part. So today I will basically show it with an assembly. So that's basically, we will start the lecture session and then we will continue our discussion with the concept of stresses that comes in a material, which will be using uniaxial load, bending load, and twisting load. So we will continue our discussion after that. So let me actually share the screen. Is the screen visible to all at this point? Excuse
Yes.
Yeah.
Yeah.
me. Okay. So great. So I have also uploaded some of the parts that I'm actually using in the analysis. So at this point, you can basically look at the steps and you can follow it later when you will have the models with you. You can basically, you can practice it yourself, or you can basically use those in models for your analysis as well. So what I will start today is I will start with an assembly. So I will start with the assembly and I already have created the parts which I am going to assemble. So by the way, this screen is visible to all.
Yes, it is.
Yes, sir. Yeah.
Yes.
Yeah.
Great, good. So, so basically it asks for the parts that needs to be assembled. So I will basically open all the parts that I have. I'm going to use. This is just to, I mean, these parts are basically simulating a knuckle joint. Knuckle joint basically has a fork, has an eye, pin. And what we are going to do, we will basically assemble this fork end with the eye. And I mean, this rod will have a specific hole and the pin will be connect the two parts together. So we have these three parts. I just brought all of them in one uh, view. Right now in this document, you have all these three parts shown here. So what I'm going to do, I'm going to first make sure that they are assembled properly so that the pin will go inside this fork end and then this rod. Any questions, guys? Sorry, I am not able to listen. You guys are good, right, so far?
Yeah, we're good.
Wait, Professor, are you gonna show us how to make these, or you're gonna, or we, our assignments to do it on our own?
No, I'm just going to show you the simulation steps for,
Oh,
yeah.
okay. Yeah, sounds
So
good.
I'm just going to show the simulation steps. So first I'm going to create an assembly of the parts, and then I'm going to show you the steps to simulate. So first we need to mate the parts together. So basically we have to make sure that the connections are properly defined. So basically I will start with concentric. Basically means the spin has to be concentric with the hole. Right now the diameters of these holes and the pins are exactly the same. So it has got 15 millimeters, and the diameter of the hole is the same as well. So if I just use concentric, selecting this surface and this, then basically it creates this mate, and that means the pin is now able to get inside. I have not yet defined where it should be positioned. I can basically translate uh, this part because it has not been properly constrained yet. It still can move. So now what I can do is I can apply a distance, basically saying this phase and this phase has a specific distance. So these distances I basically know since I created the part. So I know that these are basically the part, these are basically distances that the pin will be symmetrically placed in this. So once this pin is fixed, then I'm going to I will basically make this part on the rod, this rod, or which we call I, will go inside this pin. So again with concentric feature, which will be made with this. So now this part can actually be positioned and can translate, and it can rotate as well. The pin will also be able to rotate because the rotation part has not been constrained yet. So, but right now we are interested only in making sure that this part gets fixed inside this specific fork or the specific component that you are seeing here. So again, I'm using the distance constraint to make this. So right now we have got an assembly where I mean the parts are assembled, except that I want this part to be aligned such that the faces are parallel to each other. So that what I'm going to do, I'm going to pull this rod up and this part will be fixed, and the objective would be to calculate what will be the stresses that will come on this pin. So what I have to do is I have to create one last mate here just to make sure that I have a parallel constraint on the top face.
Professor, your voice keeps cutting off.
Yeah, you're breaking up, bro.
Yeah.
Okay, so what I was basically saying that I have got the parts assembled together, and the last mate that I have introduced is to make sure that this surface and this surface are parallel to each other. And the reason I'm doing this because what I'm interested to do is to apply load on this specific rod, and this part will be fixed. And the objective would be to calculate what will be the stresses coming on this pin. Is that making sense, guys?
Yeah.
Yes,
Yeah.
yes.
Great. So all my parts have been defined. Let me actually save this. So now basically what I have to do, I have created an assembly, and what I have to do is to create a simulation exercise. So I will start with the static simulation again, start with new study, static simulation. Once I do that, then you see that earlier it was only one part. Now I have got three parts. And what I will do, I will start with applying material. Then I will also have the boundary conditions, which is a displacement boundary conditions, apply the loads, create a mesh, and run the study. But the one thing that comes in addition to the simulation setup we saw in the last lecture or last lab sessions is that we have to define connections between how these specific parts are going to interact with each other. So first, let me apply the material. So I'm going to apply material, which will actually pop up a default material list. So you can select any material of your choice. Right now, I will use the default material that remains. I will press apply and close. When you say apply, you basically see all the parts have been assigned with the specific material. You can select your own material for different parts as well. But right now, I'm just showing you the basic steps. So I'm just applying same material to all the parts. Okay, so after that, what I need to do is to make sure that I define the connections between each part. So what I have to do is I have to create a we have to create a contact definition. Basically, we have to ensure that the contacts are defined properly. And how to define the contacts? You basically select all the parts. The SolidWorks has a nice feature that it actually identifies automatically what are the contact surfaces. So there are 3 contact surfaces right now between this end and the pin, between this rod and the pin, and between this this end and the pin itself. There are 3 contact points. As you can see, it has automatically detected that. And what we are going to do is to have a no penetration type. No penetration basically means no parts are going to penetrate into each other. So they will basically deform the other part, and we will basically see how the simulations or how the stresses will be developed. So I will press OK. So by default, it actually makes sure that all the parts are bonded together. So we don't need that specific contact at this point of time. This is the contact we have defined ourselves, which is no penetration. No part is going to penetrate into each other. So are you guys getting so far what we are doing here?
Yeah.
Yeah.
Any questions, guys? I'm still seeing some annotations here. So let me actually disable the annotations. Okay. So the next thing is, yeah, we are suppressing the global contact. Yeah. So next thing is we have to apply the boundary conditions. So what I'm going to do, I apply fixed boundary conditions on the bottom, apply load on the top, and we'll see how the system will deform. So we'll basically use fixed geometry on the bottom surface. So bottom part is fixed. Now I'm going to apply load on the top part. Now I will change the directions and let's say apply 10 newtons or let's say 100 newtons of load on the top. So my load has been defined, my boundary conditions have been defined, my connections have been defined. The next thing is basically to create a mesh and then run the study. So what we are going to do is we are going to create a mesh, and we use standard mesh size at this point of time. So you will see it's already meshed all of the parts together. And now if I run this study, so then we will see how the stresses will be coming in the material, how it is going to deform.
What material do we apply to all the?
So for, I actually chosen alloy steels for all of them, but you can define your own material or select your own material for individual parts. You can change the material. Okay, so again, it gives me the von Mises stress distribution. I'm just interested in knowing the displacements. So what I will do, if I actually right click on that and press edit definition, you will see that it actually gives the plots the displacements in a true scale. But if I want to look at the exaggerated or basically look to see how the formation is happening. So what I can do is I can just let me actually cross that and go to this plot first. So you see the displacements are very, very small at this point of time. So I will go to edit definition and increase the scale of my display. So let's say if I press a 1E4, then you basically get an exaggerated displacement. And why I wanted to show you this, because we have selected a no penetration contact. And if you look at this, the deformation just happened with producing the gaps at the surfaces. So you will not get this type of behavior if you have used global contact, which is bonded. So if you have used bonded contact, these surfaces will never leave the contact. But here with the no penetration contact, it actually allows the surfaces to get separated. So you can also animate the response, and you can slow down basically and see that the gaps are basically getting generated between the two surfaces. And this is just a displacement plot. And you can basically also see the stresses that are getting generated in the material. So if I go to the stress plot, which is von Mises stress, we will actually see what von Mises stresses are. In this lecture, we will try to see whether we can reach that specific topic or not. But von Mises stress is basically just the concept about principal stresses. And even if you have not heard about them or not remembered them yet, we have in the last lecture, we were discussing about sigma xx, sigma yy, those type of normal stresses and shear stresses. So what von Mises stresses is basically take the combination of all the stresses and gives you one number. And that number will basically tells you whether the material is going to fail or not fail, or which part of the material is critical. For example, if you look at the eye or this rod, you see that the critical part is basically at the bottom. If you look at the fork end, you see the critical part is not at top or bottom, but at basically that specific slightly away from the center or from the top. These are basically the critical locations. So von Mises stress gives you the location where the material is getting or has the highest chance. So we will actually get into more details or discuss about this specific von Mises stress. But hopefully here, basically, I wanted to show you how you can simulate a specific assembly of parts, how you can apply loads, how you can define the contacts, and you can simulate the stresses, or you can simulate how the loads are causing the stresses in the material. Is that making sense to you guys?
Yes.
Yeah.
Any questions so far?
Can you show how to do the animation part again?
So, okay, so you can so whatever plot it is right now active, you can right click on that and just press animation. So right now this is just the stress. And if you want the displacements, you can basically do the same thing, go to show, make it active, and then you animate it. Okay.
Thank you.
Yeah, welcome. Okay, that's basically a very short exercise in SolidWorks. Because in the last week, there was one question about how the analysis can be done in the assembly mode. So I just thought to basically give a short demo on the simulation or SolidWorks simulation using assembly as well. Okay, so any questions on this, guys? Okay, so if not, then what we are going to cover in today's lecture is we are going to see how can we, so what basically von Mises stress means and how we can combine the stresses that we have learned so far, which is the normal stresses and shear stresses, how they can be combined, and they can be combined, and we can calculate, or we can estimate the presence of or estimate the value of von Mises stresses. So that's basically what we will try to cover in today's lecture. I'm not sure whether we will have sufficient time to go to the von Mises stress description, but if not today, then for sure in the next lecture we will cover that part. But if there are no other questions, then I will switch to the document camera. And we will resume our lecture from here onwards. Okay. So continuing our discussion in the last week, what we were basically discussing is how can we represent the stresses. And what we have learned so far is that the stresses are represented in 3D coordinates first. for an arbitrary shaped body under general loading conditions. So what we basically saw is that if you have an arbitrary shaped body and you have different types of forces coming into it, along with movements or torques, then a stress at a point in a material is represented by a cube that has got 6 faces, and each face has got a specific set of stresses coming in it. So if you remember from our last discussion that one of these faces will have got a normal stress, and then there are 2 shear stresses for each one of these faces. Is it making sense, guys? Are you remembering what we have discussed earlier?
Yes.
Yeah. So that's what we actually saw in the last lecture. And we also saw that basically each 6 faces will have now 18 components, but only 6 stress components are independent. Three of them are called as normal stresses, represented by the variable sigmas. And there are 3 more components which we call as shear stresses, represented by the variable tau. Okay, so that's what we actually discussed. And thereafter we said that we do not need to worry about 3-dimensional state of representation or 3-dimensional representation of stresses if we can squeeze this cube into a planar form. So if one of the dimension is squeezed, then what we actually end up with is only 3 components of stresses. So for example, if I squeeze the z-axis, such that all the material is left with only confined to one plane, then what I have are 3 components of stresses on sigma xx, sigma yy, sigma xx here again, sigma yy, and tau xy, tau xy. So these are the only 3 components of stresses that remain if I can squeeze the material in one direction. So if I squeeze the material in the z direction, I only have the stress state represented in a planar form, and that's we call as planar representation of stresses. And what it basically means that all the out of plane stresses are 0. Okay. Let me know, guys, if you are understanding and you're following it so far, or you are basically not following it at all.
It still makes sense.
Still with you.
Everybody is with me so far. I mean, I am asking everybody here so that all of us are on the same page.
Yeah.
You just slow down a little bit. I'm like trying to keep up with the notes.
Okay. Yeah, I'm sorry I did not scan these documents yet. I promised you to scan the last set of documents in the beach board, but somehow it slipped out of my mind. So I will try to scan them, the last lecture's notes and this lecture's note as well. So basically you won't miss anything. Okay. So just for an example here, I'm now just taking a uniaxial load case just like we did earlier. So I have a small rectangular strip and a load is applied, a uniaxial load is applied. This end is fixed. And what I actually said that if I would like to represent the stress at point A, which is on the top surface. By the way, as just to remind you again, the stresses and strains are always defined with respect to one point. It is not for the whole body. So if there is a body, basically it is a rectangular strip and you are applying a load to it, you cannot say that the stresses in this body is given by P divided by the area of cross section. No, that will be a wrong statement. Stresses and strains are always defined at one specific point in a material. So this is an arbitrary shaped body. I basically represent a stress at one specific point, one specific location. So it is basically represented by this specific cube. So when I zoom on this specific point, I get this cube. So always you have to remember that stresses are defined not for the whole body, but for one point. Similarly, if I have a rectangular strip, I would like to find the stresses at this point A, and my coordinate systems are defined so that this is your x-axis, let's say. The one that is going there down on inside the plane of the paper is y-axis, and this is your z-axis. So if I have to find the stresses on this point A, if I take a small section of the material and try to find the stresses, basically what I'm going to do is I will zoom that part out and say the stresses would be represented by a plane, which is X here and Y. This is for point A. Similarly, if I have something for point B, which is lying on this surface, this side, and I have to zoom that, then the stress will be again represented by a planar form where this axis will be X and this will be Z. Is everybody following it so far?
Yep.
Yeah.
Yeah.
Yeah. And since it is only uniaxial load, so in this case, I only have sigma xx sigma xx. And here also I have only sigma xx. Uniaxial stresses will be present because of uniaxial load. There will be no other stress component present. So sigma, the other components would be sigma zz and tau xz. You guys getting what I'm saying in this?
Yeah.
Yeah.
Okay. I'm not sure whether you're still following it or not, but let me actually ask someone from the class and see if it is making sense to everybody. Can I have Daniel Lim? Daniel Lim. Okay, let's say Hannah Kotov.
Sorry, Professor. Mic wasn't working. What was the question?
So is this Daniel?
Yeah.
Okay. So Daniel, what I said that generally speaking, the stresses are always represented in a three-dimensional form. So this is in three-dimensional form, 3D space. But as an engineers, it is very difficult for us to solve the problem in three-dimensional. So we as an engineers try to approximate them and try to represent that in a two-dimensional planar representation, where one of the plane or one of the component of the, one of the uh, axis is squeezed. The material is squeezed in one direction, basically. So if I squeeze a material in Z direction, I get the stresses in one plane, which is basically given by this specific representation when I squeeze this material. Are you with me?
Mm-hmm. Mm-hmm.
And this material will have now only three components: sigma xx, sigma yy, and tau xy, right?
Mm-hmm.
Right? Now I said that I have a uniaxial beam, a beam or rectangular strip, which is under applied load. And I want to represent the stress on this specific point. So what I'm taking, I take a small surface at that and try to represent it using this form representation. So what I'm basically showing is x-axis and y-axis, because this surface is lying on the top. Yeah.
Yeah.
So this is exactly the same as this x and y, where you have got sigma x. What other components will be coming on this component, on this area?
The
So
tau.
I have got one normal stress sigma xx, and then I will have what? Just like I have here sigma yy, I should have sigma yy as well, right?
Uh-huh.
Right?
Yes.
So what other component would be there? What I'm missing here?
The tau.
Tau, right? So their shear is there. That is what I have not represented. Now this is for generic case. Generic case means generic loading case. For our uniaxial load case, I know only sigma xx is present. These components are zeros because they are not present in the material at this point of time. Neither sigma yy is present, neither tau xy is present. Are you seeing what I'm saying?
Mm-hmm.
So here I only get sigma xx. Sigma yy is equals to 0 and tau xy equals 0. So that's why I'm not representing it. Is everybody getting it so far?
Yeah.
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 Okay, so let me ask somebody else now. Alan Roas. Alan. Bennett Weiss. Okay, not present. Then Austin Mock. Okay, none of you are present. So what's that? Oscar. Are you guys in the class or you are just logged in?
I'm here.
I'm here
Logging.
too. I'm here.
Okay.
Here.
I'm seeing
Brad
91
Austin's
participants.
name. And Austin's mic isn't working.
My mic, okay, when I tried. Okay, no problem. How about Trevor Norman?
I'm here.
Great. So can you help us to say what will be the other stress components for this surface or this element, stress element? So this is a stress element which I am zooming in from this point and drawing it here. And this has got x-axis, this has got z-axis based on the representation. So I already made that sigma. I also said, showed in the figure that sigma axis will be present. What other components will be there? Should have been there. Just like here, just look at this.
So I guess sigma,
Yeah.
it would be sigma YY.
No, it will not be
Or
sigma
sigma Z.
right now. It will be now sigma ZZ. Because we are talking about Z axis, right? Normal stresses in the Z direction. Do you see what I'm saying?
Yeah.
So, and what will be the shear component called as?
So that would be
Tau.
tau Y, wait, tau XZ.
Tau XZ, perfect. So that's it. That means you are now you guys are getting it. So if I am in X and Z plane, there will be no component of stress in the Y direction. If I am in this XY plane, there is no component of stress in the Z direction. Are you guys getting what I'm saying here?
Yes.
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 That's what we call as planar representation. Planar representation means in this plane, XY plane, I only have stress that has only X and Y component. There will be no stress component that has got a Z as a subscript. There will be no tau xz, there will be no tau yz, there will be no sigma zz. All the stresses out of the plane will be zero. Similarly here, the plane is xz. So everything which has got subscript y will be zero. Everything else will remain. Now in this specific scenario, I know again that because my load is uniaxial, I don't have sigma zz and tau xz. So basically again, I can represent it by this way, this sigma xx only. So here I have tau xz equals 0 and sigma zz equals 0. Are you guys with me so far?
Professor,
Yep.
good question. How come there's no tau xz if tau xz is like going in the same direction as the force P?
Which way?
Like the tau xz on the one on the top? Yeah, like that
The
one.
tau. So you have to remember that the shear is basically coming if there is some sliding in the material happening. So if the load is uniformly distributed, then all of the strips of the material are sliding the same fashion. So if I have a small strip of material, and again I have a small strip of material, they are all getting elongated at the same proportion. So unless there is some relative slippage happening, there will be no shear stresses.
Okay. Yeah, that makes sense.
Okay, cool. So this is, I mean, even if we have no shear, but that is valid, that statement is valid only when the stress element is oriented in the direction of my load. If my stress element is now rotated by a certain angle, then I will have both tau xz, sigma zz, and sigma xx. Do you see what I'm saying? If my stress elements are oriented in the direction of my load, then only I can say my tau xz and sigma zz are zero.
Professor,
Yeah.
is that new diamond that you drew, is that still on the same face as B?
Yes. Yes.
Okay.
It's on same face as B, but because it has got oriented, I want to see what will be the stress components on this specific element when it has been rotated by a certain angle. So if it has
Okay.
by a certain angle, how can I find the stresses? And there we actually need the Mohr circle concept. I don't know how many of you remember or have seen the Mohr circle, but what we are going to do today is basically see how can we quickly plot Mohr circle. So what the Mohr circle concept says that just like you have, so everybody knows about x-axis and y-axis, right? The concept
Yes.
x-axis and y-axis, the horizontal axis and vertical axis, everybody understands this much, right?
Yeah.
Yes.
Yeah.
Yep.
So horizontal axis, we actually in Mohr circle case, we represent the horizontal axis as a normal stress. So all the stress components which are normal like sigma xx or sigma zz, they will be marked in this horizontal axis. Okay. So positive here and negative here. We all know positive stress means tensile stress. We all know negative sigma means compressive stress. Everybody is agreeing with that part?
Yes.
Okay, on the vertical axis, we are going to plot or mark tau, the shear stress, and CW and CCW. What is CW and CCW means? CW means a component of stress, shear stress, that has a tendency to rotate clockwise, and the component of the shear stress that has a tendency to rotate counterclockwise. So if I ask a student here, let's say, set set. Okay, Sean.
Hello.
Yeah, hi. So can you tell me what is the tendency of this shear stress to rotate this element? Is it going to rotate it clockwise or counterclockwise?
Counterclockwise.
Counterclockwise. So if I see at this point, I have got sigma xx and tau xy. So what I will do, I will actually plot 2 points, sigma xx, let's say this is positive, and tau xy, that since it has a tendency to rotate counterclockwise, so that will be, it will be marked at this point at the bottom. So tau counterclockwise, tau xy that has a tendency to rotate counterclockwise will be marked downwards. So here I am getting 1 point, which is tau sigma xx and tau xy. Is everybody with me so far?
Can you?
Can you say it one more time?
Yeah, I kind of.
So let me actually give you some numbers here. So sigma xx is, let's say, 5 units, newtons per millimeter square, say. These are all hypothetical numbers I'm making up just to make sure that you understand the construction of Mohr circle. Sigma yy is, let's say, 2 newtons per millimeter square, and tau xy comes out to be 3 newtons per millimeter square. These are the numbers you are getting. Okay, these are the numbers you have calculated from the loads, applied loads. For example, in this case, if P is 10 newtons and cross section area is 1 millimeter square, what will be sigma xx? P divided by area, 10 divided by 1, which will be 10 newtons per millimeter square, right?
Yeah.
Are you with me? Are you guys with me? How do we get this sigma xx and how can we calculate sigma yy and tau xy for depending on different loads? So depending on the load and the specific geometry, you can calculate sigma xx, sigma yy, and tau xy. So for, let's say you are given these represented, you have been calculated and you said that sigma x is 5, tau xy is 3, sigma yy is 2. So if these are the numbers, can you draw a Mohr circle for this specific stress element? So that's what I'm right now showing you, that what you have to do is you have got 2 points. One is got sigma xx, tau xy, CCW counterclockwise, and you got sigma yy and tau xy clockwise. So on this phase, the tau is going to rotate the element in a counterclockwise fashion. So I'm going to basically mark this point on this coordinate system, which is 5 and -3. Actually not negative, we will say 5, 3 CCW. Are you guys with me?
Yes.
So
Yeah.
what other point we have to use? Sigma yy and tau xy. On this phase, the tau has a tendency to rotate clockwise. So if sigma yy is 2 units, which is here, let's say 1, 2, 3, 4, 5. So 2 and 1, 2, 3, 1, 2, 3 here. So 2 and 3. 2 and 3, and 3 will be upwards because this has the tendency to rotate clockwise. So 2 and 3 will basically be marked here. So this will be your sigma yy and tau xy. Yeah.
Yes.
Yes.
Everybody is with me, or you guys, anybody who has missed it, please let me know. I'll try to explain again. Yeah.
Could you just move it down a little bit, please? The paper?
Down means.
Oh, no, I mean up. Yeah. That way. Okay. I see it.
Is there anybody who is not following it or who has missed something? I will try to explain again. Okay, so everybody has been following it so far.
Yeah.
So we have just marked 2 points. What you need to do is you just join these 2 points using a line. Okay. And wherever this line intersects this axis, that becomes the center of the Mohr circle. And this specific is quantity from center to that point, or from here to here, that will be the same. That will be your radius. Now you take that, you take the compass and you basically draw a circle. And that basically completes your Mohr circle construction. Well, that is not exactly a circle because I'm not using a compass, but that circle will be your Mohr circle. Is everybody following it so far?
Yes.
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 Everybody is with me?
Yes.
Any questions, guys? Okay, so if not, then I will actually again try to do the same thing on this sheet of paper and tell you then why we actually care about this. What is the need of doing all this construction, and why do we actually, why it matters? So right now, as I said, I have got planar representation of stresses. This was sigma xx, which was taken as 5 newtons per millimeter square. Sigma yy, I consider that as 2 newtons per millimeter square. Tau xy, which is 3 newtons per millimeter square. Okay, so far, again, it doesn't represent a circle, but at least you guys know that this is the center and this is your radius of the Mohr circle, okay? Now, when this circle intersects this axis, x-axis or the sigma stress axis, can anybody tell me what is the value of shear stress in that position?
That'll be 0.
0, right? And what will be the value of shear stress in this location?
0 as well.
0 as well. So these are the points which we call as principal stresses. So this has got coordinates sigma 1, 0 and sigma 2, 0. Sigma 1 and sigma 2 are basically the principal stresses. So principal stresses by definition are the stresses are the stress components, are the normal stress components acting on a plane that has got shear, that has got 0 shear. Okay, does everybody follow what I'm saying here?
Yes.
So far.
So far, you are okay with that right now? So when I say, let's look at the statement again. Principal stresses are the normal stresses. So again, when I'm talking about these are the horizontal axis. This is your normal stress axis. So any axis, any stress component, which is a normal stress component, will be plotted in this axis. Any stress component, which is called shear, will be plotted in this direction, in the vertical direction. Horizontal directions are for the normal stresses. Vertical direction are for the shear stresses. So once I get a Mohr circle done, and as I said, Mohr circle is basically you draw a straight line connecting these 2 points. How do you get these 2 points? It is basically defined by sigma xx and tau xy and sigma yy and tau xy. And here you actually see whether tau xy is clockwise or counterclockwise, and that's basically will tell you whether you have to plot this mark down or up or bottom or up. So that will tell you whether it is in the counterclockwise fashion. Tau xy has a tendency to rotate the element in a counterclockwise fashion, or the shear stress has a tendency to rotate in the clockwise fashion. So that will be determine the direction of this point. Now, when you got these 2 points, you join using a straight line. Wherever this line intersects this axis is called a center, and the radius will be basically this distance from center to this point, and from this to this point, these will be the same. So that will be your radius. You basically construct a circle out of that. Wherever this circle intersects the horizontal axis, at this point, the shear stress components are 0. So the principal stresses or the value of the normal stress are basically called as principal stresses in this scenario. And this angle, which is given as twice 2 theta p. 2 theta p basically means if I rotate this stress element by an angle theta p, let's say this angle comes out to be, say, 45 degrees. Say, looking at the construction, let's say it is 45 degrees. So what it says that if I rotate this element by 22.5 degrees, half of that, because this is 2 theta p. So if I rotate this stress element by 22.5 degrees, like this, so if I rotate it by 22.5 degrees, then in this representation, I will not have any shear stresses. I only have normal stresses given by sigma 1 and sigma 2. There will be no other stress component. There will be no shear component. Okay, this is 22.5 is coming from half of that because this is 2 theta p. So basically it says that if you rotate this stress element by 22.5 degrees in the counterclockwise fashion, because you're rotating in counterclockwise. So in the rotating in counterclockwise by half of this angle, in this angle, if you draw the stress element, then this stress element will not have any shear component. Is that making sense, guys?
Yeah.
Yes.
Any questions on this?
We had a student in chat ask if it's always rotating counterclockwise.
So it depends on how this angle you are basically defining. So if your point is marked below, then yes, you always have to rotate counterclockwise. Is everybody with me so far?
Yes.
Okay, so now I come back to our original question and asked you that if I have a uniaxial load case like this, and I have this representation of stress at point A and at point B is given by, this is your x axis, this is your z axis, and this is your y axis. So if I have to basically take a stress element at point B, and I know that only stress component that is acting here is sigma xx, which is given by load divided by the area, cross-sectional area. If the area is, if load is say 10 newtons and area is 1 millimeter square, so 10 divided by 1 will be 10 newtons per millimeter square. So in this specific scenario, can you draw a more circle if you understand so far? Okay. I'm giving you a couple of minutes. So we'll just come back in shortly in 2 minutes, 3 minutes. And by that time, please try to construct a more circle for this specific scenario. Okay.
Could you move your paper up again, please?
Up or down?
Thank you. Yeah, that one's good.
Down?
No, it's good now.
Okay.
Thank you.
Yeah. Okay, guys. So done on this more circle.
I tried it.
Yeah.
Do it together. So what are the two coordinates that you need or you will get?
I got 0, 0 and 10, 0.
Yeah. The two coordinates will be dependent on sigma xx, tau xy. That should be one coordinate, one point. Let's call it as A, point A, and point B will be sigma yy and tau xy. What is the value of tau xy in this scenario?
Be 0.
0.
Zero.
And what is the value of sigma yy?
Also 0.
0, right? Yeah. So I got 2 points, 0, 0 and 10, 0. So let's say this is one point I got, which is point B, and 10, 0. So let's say this is 10, 0, which is 10, 0. Okay. So let me actually ask somebody, Ryan Hagen.
Yeah.
So what will be the center of this Mohr circle then?
5, 0.
Yeah, it will basically the center of this line, which will be your center of the Mohr circle, and the radius will be
5.
5. Perfect. So now you know how to construct a Mohr circle for this scenario, and it will be basically, I'm always overstepping on this. Okay, let's say this is your point A. Okay, this is 5 and this is 5. So what will be the principal stresses then?
sigma 1 would be 10.
Yes, perfect. So sigma 1, this will be sigma 1 and this will be sigma 2, right? So basically what it says that in a uniaxial load, this element, stress element itself is basically a principal stress because there are no shear stress acting on it. Okay. Now, can somebody tell me what will be the point at which the shear is maximum? Shear component is maximum.
Would that be 5.5?
So actually, let me ask that in this circle, what will be the point at which the shear component is maximum? Which point has got the shear maximum?
It would be the point right above the center of the Mohr circle.
Here?
And it could also be the point below it.
Or the point below it.
So both of them are basically the same, has got the shear maximum. So we basically look at first the positive part. I mean, both of them have got the same maximum shear stress. This is the maximum shear stress. And at what angle that maximum shear stress is happening? So if you see, this is the principles, this is the plane on which the stress is acting. And this angle is -90 degrees. And if I rotate my stress element by half of this, because this angle is 2 theta basically means if I rotate this stress element by half of that, I will reach a point when I will get a maximum shear stress component, right? Are you guys following what I'm trying to say here?
Could you say that again?
Yeah.
So if I rotate this element, stress element by 45 degrees, I rotate this element by 45 degrees, then whatever the stress components that are coming in here, that will be given by these points. What is the normal stress in this, at this location?
Maybe
5.
5.
5. So the coordinate of the stresses are 5, 5. Basically, it says that the normal stress would be 5 and the shear would be 5. So I am in this specific orientation, I have got shear stress and normal stress, both of them acting. And both have got the same magnitude. Now, the reason what I wanted you to actually pay attention to here is that why we care about that. So if this rod or this thin strip of material is made up of aluminum alloy, which is ductile material, or it is made up of a ceramic or a glass or maybe a carbon fiber, which is brittle, which is not as ductile as aluminum. It is made up of two types of materials. Now, in these two types of materials, if the load keeps on increasing, eventually this material is going to fail, right? Everybody agrees with me on this part?
Yeah.
Yeah.
If I keep on applying the load, the material will fail. Now, let me actually say that ductile material fails and ductile material is weak in shear. And brittle material is weak in tension. Okay, so that will define their failure mode. So if a material is ductile materials will always fail along the planes where the shear stress is maximum. And brittle materials will fail along the planes where tensile stresses are maximum. So if this material is made up of aluminum alloy and you are applying this load, and you know that this material, because it is ductile, it is weak in shear. So in which plane do you think the material is going to fail? Is it going to fail like this, or is it going to fail in 45 degree plane? Which plane will have maximum shear? Repeating my question.
Fail at the 45 degrees.
But yeah, so you actually see there that the maximum shear stress is coming at 45-degree plane. 45-degree because it is half the theta is 90 divided by 2, it's 45 degrees. So if you rotate the plane by 45 degrees, that means you will see that ductile materials will actually start necking in 45 degrees. So if you have seen a uniaxial test, you will basically see that the material will fail like is basically getting cleaved, having a plane in 45 degrees. It basically breaks in 45-degree planes. So if you actually have seen, it will actually fail like this. That is a failure of ductile materials, and they will basically fail because they are weak in shear, and along these planes, the necking will happen and they will fail. Is that making sense to everybody here?
Yeah.
I mean, if you have seen, if you applied a uniaxial load, if you have done an experimental class or testing class, you probably have seen that when you apply the load, you actually see the necking occurs, and necking occurs in 45-degree plane. And that the reason why necking occurs because this is the plane at which the shear is maximum when we apply a uniaxial load. This shear is maximum along 45-degree planes, 45-degree to the you applied load. And that is why you basically have this type of failure that takes place. Is it making sense to everybody?
Yep. That makes sense.
Yeah. And let me ask someone from the class. Sovan Priya.
Yes, sir.
So if the ductile materials are weak in shear and the shear is maximum along this plane, that's why they will fail. What will happen with the ceramic materials? How will they fail?
I'm sorry, could you repeat your question one more time?
So what will be the failure mode looks like for ceramic materials or brittle materials?
It would kind of just be like broken.
So yeah, it is weak in tension. Tension basically means along the normal stress plane. Normal stresses are maximum at what plane? At the 0, 0. It is basically the same plane along which the normal stresses are maximum. So basically when you see the brittle materials will fail like this. Will fail like this. And this is the load you are applying. This is the load you are applying. And because the stresses are maximum along this specific plane, the normal stresses are maximum along the 0-degree plane, along this plane, which is 0 degree, which is aligned with the load axis. So the ceramic or the brittle materials, which are weak in tension, they will fail along these specific planes.
Got it.
Yeah. Are you guys getting what I'm trying to convey here, or what message I'm trying to convey?
Yes.
Yep.
Yes.
Yes.
Yeah. So that is the whole purpose. We are just trying to understand what is sigma xx, tau xy, why we care about more circle, principal stresses and planes. Eventually everything will be tied to this failure of a material. Because as we said at the very beginning, that as a designers, our objective is to make sure that the material should not fail under applied load or during the surveys. So how can we prevent failure? Before we actually design something to prevent failure, we have to understand how the failure happens. And to understand that, you have to understand what we are talking about, the stresses, what are the different components, how the stresses can be represented in a more circle form, and where we are actually getting the maximum principal stresses, where you are getting the maximum shear stresses, and that will tell you how the material will fail in service. So that is the whole purpose of studying this specific concept. Is that making sense, guys?
It is.
Yeah.
Yeah.
So just to like make sure, so the aluminum would fail at the 45, right?
Yes.
And the brittle material, like ceramic, that one fails first when it's straight.
Yes.
Okay. Okay.
So if you look at the stress element at this point, you have got sigma x, which is the equals to sigma 1, which is equals to 10. And this is sigma 2. This is the maximum. This is the maximum normal stress component. And if you look at this, you will basically see this is the same plane as that, which is get the maximum shear stresses, which is oriented at 45 degrees. Does it make sense?
Yes. Yes.
So that is what you are seeing here. And this specific scenario is happening over here when you actually translate this back to this point. This is what you are happening here. So that basically tells us that if you have an uniaxial load and the material is ductile or whether the material is brittle, how the failure will happen, you can easily tell by looking at the Mohr circle and say where the maximum principal stress is happening or where the maximum shear stress is happening. That will define my failure of the material.
Professor, I have a question.
Go ahead.
Will it always fail in the middle of the length?
No, it will never, you can never guarantee that, but to make sure that it fails, what people do, you actually make a specimen like this. If you have done the tensile testing, you will probably see this is called a dog bone specimen. And the reason is that this has got narrow section. This is the place where your grips comes. Applied load. This is the place where grips come. And this is a narrow section. So stresses are basically concentrated in this narrow section. So that's how you basically can make sure that the failure will basically takes place in this region. Does it make sense?
Yes.
So you basically, when you are doing the testing, then you are controlling the specimen geometry to make sure the failure takes place in the gauge length. So this is called as gauge dimensions or gauge length. Gauge length basically means this is the dimensions where you are actually recording the stresses and strains, and you make sure that the failure happens at the middle point, middle section basically. In reality, or in actual applications, when you do not have any control about the shape or geometry of the testing, you do not know where the failure is going to take place, but you can always be sure that if the material is ductile, they will always fail in this 45-degree place. It can happen in anywhere in the material where the stresses are maximum. Just like as I was showing you in the SolidWorks simulation, that you do not know at what location the stresses will be maximum. It will be dependent on different type of loads and different types of geometry and how the deformation is taking place. So looking at the simulation, you can tell which specific location is critical, and in that location, the stresses will cause the failure in the material. Okay, guys, any questions so far? Okay, so this is a very simplistic case where you only have uniaxial load. What will happen if you have a bending load or you have a twisting load? In those scenarios, you will never have the case where sigma tau xy will be 0 as well, or sigma yy will be 0. But let's say, let's wrap up this today's lecture with a specific scenario about a bending load. For example, you have a cantilever beam, or rather a simply supported beam, let's say. So this is the cross section, rectangular cross section, let's say 1 millimeters by 1 millimeter cross section. And you have the load. And I'm interested to find the stresses at a point which is on the top surface, but near the load. So if I have to represent the stress element at that point, okay, let me actually make a 3D representation as well. So this point A is the top surface. If I have to represent the stresses at that point, I am basically representing it by this plane. Okay, so can now somebody volunteer and tell me what will be the stress components that will be acting on this stress element, which is on the top, lying on the top surface?
We would have a sigma XX.
Yeah, perfect. And
Sigma YY would be 0.
yeah, sigma YY will be 0. And what about tau XY?
I want to say it would be 0 as well.
Why do you want to say? I'm not sure.
Just because it's in the our areas in the ZY plane.
We are basically on top surface. So basically that means that tau XY will be 0. Just like we actually discussed in the last class, that tau is maximum at the middle. So on the top, the tau is basically 0.
Okay.
So this is exactly the same representation as our uniaxial load scenario. You have only sigma xx. But if I'm looking at point B, which is in the middle, then I have a different stress representation. This will be X, this will be Z. And in this scenario, I will again have sigma XX. Or do we have sigma XX in this scenario or not? Can somebody tell me what will be the stress representation for the point B? Anybody can volunteer?
Would it still be normal XX?
If you look at this, sigma xx will become 0 at the middle. So that means that there will be no sigma xx. Okay?
Okay.
So what else will be there?
Is it normal ZZ then?
Okay, so let me ask you, will there be sigma zz in this case?
Yes, because the
somebody-
force is going downwards, right? It's going in the Z direction, the force peak.
Okay, so that is what you have to be careful about. So force is going in the Z direction does not mean that it will cause these stresses in the Z direction. So always, so this is the mistake we always do when we see that the direction. So we actually get confused with this specific application. So when we see that load is in this direction, so sigma x's will be in this direction. So this is true only where for uniaxial load case. This is a uniaxial load case. Okay. Here it is a bending load. So to differentiate between that, you always have to think how the deformation is happening. So when you're applying load like this, what is going to happen? This is going to stretch, right? This is going to stretch. Are you seeing what I'm saying?
Yeah.
So when it's stretching, then you have sigma x in this direction. But when you apply load from the top, what is going to happen is it's going to basically deform like this, right?
Mm-hmm.
So then basically what means that the top part will be in compression, bottom part will be in tension. Agreed?
Yeah.
But in which direction this is happening? I mean, in which direction they are shortening and lengthening? In which direction this is happening? In which direction I am feeling stretch, shortening of the fibers, and in which direction I am basically feeling the increase in the length of the fibers? Is it in the X direction, in the Z direction, or in the Y direction?
Well, would it be in the X direction?
Always in the X direction, because you are basically seeing that this is basically getting stretched in the X direction and compressed in the X direction. So it could be anything in the Z direction. Even if the load is acting from the top, You don't have to worry about the load. You have to worry about how the deformation is happening. That's what I mentioned briefly in the lab as well, that all finite element simulations, they tend to care about the deflection, the deformation, and that will tell you how the stresses are coming. So if you look at this, that deflection is happening like this. So that is, it is shortening in the x direction on the top. It is increasing in the length in the x direction at the bottom. So all the stresses are basically happening in the x direction, even if the load is coming from the top. Are you getting what I'm saying?
Yeah.
Yeah. So now coming back to my original question here, what will be the stress representation looks like?
So if it's stretching and compressing in the x direction, then you'll get forces in the x direction, right?
You will get sigma xx, but because this is in the middle, sigma xx is 0.
I have a lot of my friends.
Right? The bending stresses are varying like this because it has got maximum at the top, maximum at the bottom in other direction, and 0 at the middle. So sigma xx is 0. So what else is remaining then?
Is it tau?
Tau. So yes, the only thing that is remaining is tau. So tau xz is the only stress that is remaining. You see what I'm saying?
So it's only like there's only gonna be a shear stress then?
Yeah, for this point, there will only be shear stresses.
Okay.
On the top, there will be only normal stresses, right? And if I take about any other point C, there will be different combination of sigma xx and tau x. So if somebody asks me that, okay, if I have a stress element at point A that has got uniaxial stress like this, I have got a stress element at point B which has got only shear stresses, how the material is going to fail in this scenario? If somebody asks me, okay, so you know about the stresses, okay, so great, then how the material is going to fail? What will be the answer for me? The answer will basically depend on, can I construct a Morse circle and find the principal stresses? Because that will tell me whether the principal stresses are maximum at point A or whether it is a maximum at point B. Do you see what I'm saying? Do you guys see what I'm saying here?
Yeah.
My question or my answer would based on what type of material first I am looking at. Am I looking at ductile materials or am I looking at brittle materials? If I am looking at ductile materials, then I'm concerned about maximum shear stress. So I will only look at where the maximum shear stress would be maximum, whether it is maximum at point A or whether it is at point B. So I will try to draw a Morse circle for point A using this element. I will draw a Morse circle for point B using this element, and then we'll find out which point has got the maximum shear stress. And that point will be my critical points.
Okay.
If the material is a brittle material like carbon fiber composite or ceramic or a glass or cast iron or something else, then I will say, okay, in these 2 points, my Morse circle, what my Morse circle tells about the maximum normal stress, principal stresses. And wherever the principal stresses are maximum, that point will be my critical location. Does it make sense?
Yes, it does.
So what we are trying to do here is, under the combination of different loads, whether it is bending or uniaxial or twisting, can we combine these stresses in a form that will tell me how the material is going to fail? And that is basically what we are going to learn next, is how can we define or describe the failure of a material. So that we will actually start covering in the next week lecture, and we will talk about that von Mises stress. So as I said, that probably we may not have the time to discuss about the von Mises stresses. So next week, we will continue our discussion about the von Mises stresses and see that what it is, how it helps us to determine the failure of a material, and how it will help us to determine at what plane the failure will take place. So that's basically we will start covering in the next lecture. But let me know if you guys are getting the basic motivation behind these topics.
Yes, it's
I
understandable.
believe so.
Okay, great. Any questions, guys, before we wrap up today's discussion? So if not, then I'm quickly going to wrap up what we have discussed and to reiterate. So what we actually saw that we, instead of looking at the stresses in 3-dimensional, we are looking in the planar form, in 2-dimensional form. And in 2-dimensional form, we actually got 2 points, sigma xx and tau xy. Depending on how the tau xy is going to rotate the element, whether it will be counterclockwise or clockwise, we have this label as well. Then on this representation, we actually put the normal stresses in the horizontal axis, shear stresses in the vertical axis. Shear stress clockwise direction would be pointed upwards, counterclockwise will be pointed downwards. So I use these 2 points to mark in this coordinate system. Once I get these 2 points, I join them with a straight line. Wherever they intersect becomes a center, and the radius becomes this from point C to that point becomes a radius, and then use this radius to construct a circle. Wherever the circle intersects the horizontal axis, that becomes your principal stresses. And when the circle basically says what's the maximum component of the shear would be, that will give you maximum shear stresses. Now, depending on whether the material is ductile or brittle, you have to worry about this point or this point. If the material is ductile, you have to worry about this point. If the material is brittle, you have to worry about these points. Okay, so that's what we are basically doing in this thing. So we are applying a uniaxial load, and we saw that if the material is ductile, I'm concerned about this maximum shear stress that happens at 45-degree planes. So I actually saw that, okay, I actually found it experiments that this is how the necking happens. But if the material is brittle, then I'm worried about these points, the max principal stress points. And that basically tells me how the failure will take place. So these are basically the discussion with the uniaxial load cases. Now we will move towards a combination of loads. If we have uniaxial load, bending load, twisting load, how the loads causes different amount of stresses and how they can be combined together into one specific form that will help me to determine the failure of a material. So that's what we will start continuing our discussion in the next lecture. Any questions, guys, so far?
And you said there's no lab this week?
No lab this week. I am just asking you guys to continue working on your projects, and I will start having the reviews next week for whatever the projects you are working on to see what is the progress you are making, and then we will have the next round of assignments for you guys afterwards. And I will be available through the Zoom. So if you guys have any questions about your project or you want to discuss anything, please email me and I will be available through the Zoom link. I will basically come in the Zoom and we can discuss if you have any questions specific to your project.